All right, welcome everybody. Just getting this to load here, and we will get started. So at the end of class, or second half of class on Monday, we were discussing buffer solutions, which y'all have some experience with in your lab. But just remember, buffer solutions, you must add an acid and its conjugate base, or a base and its conjugate acid, some conjugate pair in order to form a buffer solution. So at the end, we did this learning check, and I don't know why this isn't showing. Oh, here we go. We did a learning check where we were looking at what solutions might, or what combination of acid and base might make a buffer solution. And I don't know why this isn't working. I'm going to do a restart. So as this is getting started, go to that learning check that's after the slide that we finished on Monday. So it's a two-part learning check. The statement says that ammonia, NH3, and ammonium chloride are combined to form a buffer solution. And we're given initial concentrations of ammonium and NH4+. NH4 plus compared to NH3, notice that it has gained a hydrogen, it's gained a plus charge. So that would be the acid version of NH3. So we have a conjugate acid-base pair. We have the Kb of NH3, and then we're looking to find the pH of that buffer solution. Keeping in mind the goal of a buffer solution, when you create it, is to resist a change in pH. So knowing what the pH is of the buffer solution is a key part of using that solution. So let's say we've added NH3, we've added NH4, we've created a buffer solution. With those certain concentrations of NH3 and NH4, we're looking to calculate the pH. So let's see if I can get this to work now. Okay, it's not working, but I'm gonna have you all get started. One important part is NH3 and NH4Cl. Well, NH3, we're given the Kb of NH3. Oh, maybe it'll work now. Awesome. Okay. I spoke too soon. There we go. All right, so NH3, if we add that to solution, buffer solutions are made usually in water. So if we add NH3 to solution, it will act as a base. We've seen NH3 as a weak base, and it will form NH4 plus and OH minus. So it takes a hydrogen from water. That's if you're just adding NH3 as a base, but NH3 and NH4 plus are added to the solution, meaning a buffer was created. We've added both the base and the conjugate acid. So now, if we're looking to calculate the pH of a weak base, weak acid solution, we need to calculate concentration of OH minus or H3O plus at equilibrium. And so if we're given weak acid or base information, then we've in the past used an ICE table to find equilibrium concentrations. So we're going to start with that. We're going to use what we've done in the past, which is creating an ICE table to determine equilibrium concentrations and then calculate pH from that. So in our ICE table, we'll have NH3, I'm going to add H2O, but as you all know, we ignore it because it's a liquid. It doesn't influence equilibrium at all. We have NH4 plus and OH minus. And then we're provided initial concentrations of NH3. This is 0.21 molar, and NH4 is 0.14 molar. And then OH minus we will assume is 0. Because OH minus is 0, the reaction to establish equilibrium would have to produce some OH minus to make that greater than 0. So that means to reach equilibrium, using up reactant and producing product, so plus X on the product side. And then we'll write expressions for equilibrium concentrations, 0.21 minus X, 0.14 minus X, and then just X for OH minus. So I'm going through that pretty quickly. We've done a number of ice tables before. But just filling in so far with what we had known from the problem, and then we're using these factors for equilibrium concentrations. We're going to need to find the value for X to then find OH minus concentration at equilibrium. Then we can eventually calculate pH. The only other information that we have about this system is the Kb of NH3. So we will use Kb, which is the K expression, so concentration of products, NH4 plus times OH minus divided by concentration of NH3, and that will be equal to Kb. We can use that value to then solve for X or OH minus concentration. So now plugging in equilibrium expression for each substance, NH4, OH minus in the numerator, and then NH3 in the denominator. Yeah. Yes. The top. Yes. Thank you. So for NH4, that should be 0.14 plus X. Okay, so when we have a weak acid or weak base and we're calculating equilibrium concentrations, in the past, if we had initial concentration minus X or plus X in the denominator, we can assume X is going to be really small, and so we approximate this as just 0.21. So we've done that. We did that in the last chapter. We can do the same thing for the numerator, 0.14 plus X. If X is still really small, then this is going to be approximately 0.14. So we're going to simplify both 0.14 plus X to be 0.14 and 0.21 minus X to be 0.21. So we'll say this is approximately 0.14. We still need the X value there for the concentration of OH minus. And then 0.21 in the denominator, and this will be equal to Kb, which is provided, 1.8 times 10 to the negative fifth. Okay, so use the approximations, assuming X is much smaller than initial concentrations. When it is added or subtracted, you can do that. If it's multiplied, that will have too large of an effect, so we need to keep that in there. Now we can rearrange and solve for X. So I rearranged this equation here to solve for x, and I wrote that down here. So I multiplied by 0.21 divided by 0.14, and I get x is 2.7 times 10 to the negative fifth. Remember that our goal is to calculate pH. X value gives us equilibrium concentration of OH minus. So with that, we can calculate pOH and then go to pH. So I'm going to start at the top right now. Concentration of OH minus is X, 2.7 times 10 to the negative fifth. So pOH is negative log of that concentration. And so pH is 14 minus pOH, 4.57, which is 9.43. Okay, so all of that work should look pretty familiar, right? We did this in the last chapter. Given initial concentrations, we calculate equilibrium concentrations, solve for X, find equilibrium concentration of OH minus, then we can use pOH to then calculate pH. And that was the goal of this problem, was to calculate pH. Second part of this problem, of this learning check, is to consider how would our answer change if we treat initial concentrations as equilibrium concentrations, then plug that directly into Kb. So instead of setting up an ice table, we're just going to use that Kb, which was provided, is concentration of NH4 plus times concentration of OH minus divided by concentration of NH3. And then plug in the values provided. So 0.21 for NH3, 0.14 for NH4 plus. We plug in Kb and then we solve for OH minus. So let's do that and see what we're going to get. Now this expression, right, what we have right here, we don't have OH minus concentration, we're trying to calculate that, but this is exactly the same as what we use to solve for X without having to set up the ice table. So this is a shortcut that we have when you're using a buffer solution only. So if you're just adding one component, just a weak acid, then you can't skip to this. But if you are adding the acid and its conjugate base, or a base and its conjugate acid, then you actually don't need an ice table. If we solve now for OH minus, we get the same concentration as the previous slide. So good news for you all. No ice table needed for buffer solutions. Buffer solutions only. you can assume for buffer solutions that equilibrium concentration are nearly equal to the initial concentrations. So we would still have to take concentration of OH minus, calculate POH, and then get to pH. But since concentration of OH minus is the same as the previous slide, we'll still get the same pH. But again, we don't need an ice table. Yes, go ahead, Amira.
Will it say that it's a buffer, or would we have to decide it?
So it might say that it's a buffer, it might not. So imagine this wasn't provided. I just crossed out to form a buffer. But you still saw in the problem that NH3 and ammonium chloride are added to solution. These are two things added to solution that are a conjugate pair, so that creates a buffer solution. So as long as it specifies that two things are added and those two things are conjugates of each other, they differ by 1 H plus, that means it's creating a buffer solution.
So if they're both added, like why are they on opposite sides of the equilibrium equation?
So this is how we form a buffer. Yeah, let me go back to those slides. So I drew out the equilibrium equation here, NH3 and NH4 plus. To form a buffer solution, you need that conjugate pair, and for something to be a conjugate pair, one would be written in the reaction as a reactant and one is the product. So let me go back to some previous slides. So I suppose, I mean, that's a good question. We're kind of simplifying it. So if you add, this is a previous slide where the acid, the weak acid is HNO2. If you add HNO2 to water, you get NO2 minus and H3O plus. So NO2 minus is the conjugate base. So then if you also add NO2 minus, a source, this is the source of NO2 minus, together those create that buffer because you need the conjugate, an acid and a base that are conjugates of each other. But we don't write them both like this and HNO2 on the left side because they don't react with each other. Just one is the acid, one is the base. And so one will be on the left, one will be on the right. And the reason for our problem that we're working on now, we were given Kb, so I kind of skipped over this, but this is good that we're reviewing it. We're given Kb, and remember Kb is the K expression for a base added to solution, a weak base. So I put the base version, this is base, as a reactant, and then the conjugate acid as a product. So you take one of the two things added, put it in a reaction equation with water, and then with water it should form the other species that is added. So we have NH3 and water forms NH4 plus because NH3 is a weak base. Okay. So without having the ice table, we can calculate OH minus concentration since it's a buffer solution. And then, like I said, you'd still have to continue to calculate POH and then pH to get the pH of the solution. But the next section, we'll talk about the Henderson-Hasselbalch equation, which I also think you have some experience with. This is a convenient equation that puts a lot of information together for a buffer solution so that you can directly calculate pH with one equation and without having to go through those multiple steps. So the equation looks like this. It's provided on your periodic table equation sheet. It relates the pH of a buffer solution with the Ka of that acid and then the acid and base concentrations. So for a buffer solution made with adding a weak acid HA, so I'm trying to point up there to the reaction equation, adding that to water forms H3O plus and A minus. If you take the log of this ratio, conjugate base to the acid, add the pKa of the acid HA, that will give you pH of that buffer solution. And we're assuming that equilibrium concentrations are approximately equal to initial concentrations. So this is what we showed in the previous 2 slides, that we can make this assumption for weak acid bases in buffer solution. Okay, so let's do this learning check example. So we're going to calculate the pH of a buffer that contains 0.170 molar formic acid and 0.120 molar sodium formate. We have the Ka of formic acid. So we're going to use, of course, the Henderson-Hasselbalch equation. pH is pKa plus log of conjugate base concentration over conjugate acid concentration. So I'll give you all a couple of minutes to at least plug in values. So identify what the acid is in its concentration, identify what the base is and its concentration, how to calculate pKa. Try working on this for a little bit, and then we'll, of course, go through it together. If you finish, go to the next slide. There's another Henderson-Hasselbalch question. Thank you. All right, let's plug in some values here. So pKa, if we take the pH, that's the negative log of H plus concentration, pKa is the negative log of the Ka. So we'll take negative log of Ka, which is provided 1.8 times 10 to the negative 4, and then plus log of A minus concentration. What is A minus here? Sodium formate. How do we know it's sodium formate? It says formic acid. Yeah, it tells us what the acid is. Formic acid, 0.17. Another hint is that it gives us the Ka of formic acid. So if we have a Ka of a molecule, that must be the acid. If it provided the Kb, then that would be the base. So the Ha would be formic acid. A minus, the conjugate base, is the other component, sodium formate. Another hint, sodium is Na+. So formate, which is the other part of the molecule, must have a -1 charge. And a lot of times bases have negative charges. So sodium, lithium, potassium, those are all common counter ions to conjugate bases that have a negative charge. 8 is the name, the ending for you don't have to memorize this, but just to tell you, the 8 ending is the ending of molecules that have a negatively charged oxygen. So 8 tells you that there is a negative oxygen there. So that will be the base. Formic acid, it tells you right in the name that this is the acid. So A minus concentration is 0.120. HA concentration is 0.170. So I've got 3.74 plus log of, or let's do, simplify that, negative 0.151. So really 3.74 minus 0.151, 3.59. So this equation, the Henderson-Hasselbalch equation, is another even more simple way to calculate pH of a buffer solution without having to do what we did previously. Using the KB expression, plugging in initial concentration, solving for H3O plus concentration or OH minus concentration, calculating then pH or POH. If you calculate POH, you then have to convert to pH. So lots of steps. This takes all of that, puts it into one equation. That's all you have to do. So if you see a buffer solution question and you need to calculate pH, you have initial concentrations of acid and conjugate base or base and conjugate acid, then you can plug that in. Now note that this is pKa. So if you're given Kb, then you might need to convert to Ka, which you can use Kw. So Kb times Ka equals Kw. Kw is on your equation sheet. That's the 1 times 10 to the negative 14 value. All right, let's do another learning check. We're using the same equation, but here we're trying to calculate relative concentrations of acetate ion and acetic acid. So relative concentrations, we're not looking for an absolute concentration. We're looking for the ratio of acetate ion and acetic acid. That would be A minus to HA. The conjugate base acetate ion to acetic acid, which is the acid. We're looking to make a buffer solution with a pH of 4. So sometimes the goal, like if you're working in a lab, is to create a buffer solution with a certain pH. So if the pH that you're looking to create a solution of is 4, and you're going to use acetic acid, you'd need to calculate the ratio of how much conjugate base to acid you need to add, and that's what we're calculating here. So using the same equation, try finding the value of that ratio. Okay, I'm working through the problem here. We've got 4 is the target pH, so we can plug that right in. Negative log of Ka, plug that in, I get 4.74. And then we're going to eventually solve to get just this ratio here. So I subtracted 4.74 from 4, I get negative 0.74. This is equal to the log of that ratio. And then to eliminate log, cancel out log from this equation. This is base 10, so we raise 10 to the power of both sides, and that will take away log. So we do 10 to the power of negative 0.74 equals the ratio, A minus over HA. So the ratio here is 0.18. With the information provided, we can't calculate a particular concentration of A minus and a particular concentration of HA. We're just looking for the ratio. So if you add 1 molar HA, then to create a pH of 4, you need to add 0.18 molar A minus. Or 2 molars HA would be 0.36 A minus. So as long as that ratio of the 2 is 0.18, you'll get your pH of 4. Questions on this or the previous question? Yeah. Yeah. Other questions? Okay, so this equation, like I said, is provided on your periodic table sheet, useful for calculating pHs. We're going to shift to talking about the effectiveness of buffer solutions. So if you're looking to create a buffer solution with a pH of 4, there are particular molecules that you should use to achieve that, and other factors that increase the effectiveness of a buffer solution. So these depend on 2 factors. How well a buffer solution can resist pH change depends on what we call buffer capacity. And we'll talk about each of these. Buffer capacity and then effective pH range. Buffer capacity is essentially the capacity of a buffer solution to do what it should do, which is resist a pH change. When we're talking about resisting a pH change, we're saying we have a buffered solution. You could add some acid to that solution and the pH will stay consistent within a certain range. So buffer capacity is the ability of a buffer solution to resist change in pH. When an acid or base is added. And buffer capacity is higher if a buffer has a higher concentration of the conjugate acid and conjugate base, or acid-base pair. So a buffer with higher concentrations of the acid-base pair will resist a pH change more strongly than a buffer with lower concentration. So we're comparing 2 options. Lower concentration of conjugate pair will be a worse buffer solution. It won't be as good at resisting pH change than a buffer with higher concentrations. And then effective pH range. So if you are, like I said, trying to create a buffer solution with pH of 4, then there is a group of acids that you should use, and what they are acids that have pKa's around 4. So first, buffers resist a pH change most effectively when the concentrations of the acid and conjugate base are approximately equal. So where HA is approximately equal to A minus, that would be a stronger buffer solution. And then buffers are optimally effective at a pH, so when the pH of the solution is numerically equal to the pKa of the buffer's acid. So pH is approximately the pKa of HA. And this is what you'd use to choose an appropriate acid to form a buffer solution at a goal pH, a target pH. They don't have to be exactly equal. The goal pH and the pKa don't have to be exactly equal, but buffers are useful at pH values that are within plus or minus 1 of the acid's pKa. Okay, so we'll do this next slide, the next learning check. I'll leave this on in case you're still writing, but I'll get the learning check open. You have a list of, make sure this is the right question. Okay, so you have a list of potential acids. Your goal for this question is to pick the acid that will be best suited for a buffer solution where you want that buffer solution to have a pH of 10.8. So you're going to use these two notes here. You want the pKa of the acid to be approximately equal to the pH. So of all those options there, which one has a pKa closest to 10.8? That's what you're looking for. So that's the pKa, the pKa is the negative log of the Ka.
So negative of 10 negative 5. So that's
Yes. Now one thing that might help is you're taking the negative log of the Ka to find the pKa. The pKa is close to, not exactly, but close to the value of this exponent. So the pKa of the first one, I think you calculate 4.75. That's approximately 5. You'll know that the pKa's of these acids are somewhere around 4. I'll give you that clue. These are not going to be good options. You're going to want to compare pKa's where the exponent is closer to negative 10. And that will give you, with this Ka, that will give you a pKa closer to 10.
like the news also generally copies.
About 1 more minute here. All right, 30 seconds. All right, I will close it here. Everyone submitted? Okay. So pKa of the first acetic acid taking the negative log of the Ka, 4.74. That's pretty far from 10.8. That's not going to be a good option to create a buffer solution with pH 10.8. Boric acid pKa is 9.23, so that one's better. Closer to 10.8, but still outside of that plus or minus 1 value. I mentioned we can skip the next 3. Those pKa's are going to be closer to 4. The last one, phenol pKa, is 9.96. And that's closest to 10.8. So of this list, this is the best option. Because again, its pH, or its pKa is close to the pH. Questions on this? Okay, so this next slide is another Henderson-Hasselbalch equation. I'm just going to give you the answer to this. It is 4.86. So this is something you could try on your own, see if you get that answer, and then if you don't, come to recitation or send me an email and I will help you. But using the Henderson-Hasselbalch equation, it's not much more than what we've already done. What I want to do now is shift to those review learning checks from Monday. So we did the 2 from Gen Chem 1, and then I have another question that I'll have you all do. But we'll first review the ones that you did on Monday. Oops. Okay, so this first question, we're thinking about sig figs. So going back to chapter 1, this was one of our exam questions if you were in my class last term. So we have a graduated cylinder, it's filled to a certain amount, and we're reporting the volume of the liquid with a correct sig figs. So the correct sig figs depends on what information is provided by these hash lines on the graduated cylinder. So here we can see up to the ones place. So 1 milliliter, 2, 3, 4, 5 milliliters. We don't know anything more precise. So right there, we know we have for sure 21 milliliters. The next value we approximate, and that would be the total number of sig figs. So here we can have 3 sig figs. We know for sure 21, and then you can approximate the next one, and that would be the sig fig. So 21.5 would be the correct option there. So let's see, 21.5. 3 sig figs, we know for sure we have 21, then we can approximate one more. Then next we had the ruler. So we are looking at centimeters. We have hash lines for 2 centimeters, 3 centimeters, 4, and then in between for 0.1, 0.2, 0.3, 0.4, 0.5, etc. So right here, we know at this point we have 2.7 centimeters for sure. It's a little bit before 2.8. So we know for sure there are 2.7 centimeters. We can approximate one more unit. So the correct number of sig figs here would be 3 for 2.77. 2.77 is certain, and you can have one uncertain, and that would still be considered a sig fig. Okay, I'll start the next one. If you have questions on, well, before I start, do you have questions on these two measurements? Okay, then I will start the next one. So this is, I think, from chapter 2. We're talking about subatomic particles. So you have an atom that has a charge, selenium with a 2- charge. We're going to say that the isotope that you're looking at has a mass number of 76, and you're determining the number of electrons, protons, and neutrons present in this ion. So subatomic particles are the protons, neutrons, and electrons. So just determining how many of each. And you shouldn't necessarily calculate in that order. You might calculate in a different order to what the questions are. Is it coming back? You're remembering? Yeah? A little bit?
You need to add to
Okay, I'll leave it open. We'll review it on Friday, but take whatever time you need. It's still open.